to OFDM. Let us start with the idea, basic idea of OFDM. Why do we need OFDM? Mic is okay. Cameraman है अभी आने दे cameraman को start कर So why do we need OFDM? That is the first thing we have to understand. Who can explain? So several of you must be familiar with OFDM, right? So why do we need OFDM? How many of you are familiar with OFDM? Yesterday many people said that they are familiar with OFDM, right? No, I know many people are familiar with OFDM. I'm sure that many people, well, at different levels you would have heard about OFDM, applications of OFDM, OFDM communication systems. My question is, what is OFDM? We'll come to that later. But why do we need OFDM? Why do we need OFDM? Yeah, tell me.
We can place carriers very close to each other. We don't require band gap between two carriers.
Okay, good. I'm asking at a very high level. Yeah, I'm going to explain OFDM soon, but I'm just asking at a very high level, why do we need OFDM? What is the motivation? To avoid inter-symbol interference. Yeah, what do we mean by avoiding inter-symbol? Why does inter-symbol interference happen in a wireless communication system? Why do we have inter-symbol interference? Why do we have inter-symbol? Yeah, tell me. Because of multipath. Yeah, but sir, only multipath by itself is causing inter-symbol interference, or multipath under some conditions will cause interference? Delay spread, right? What is delay spread? So you understand the concept of delay spread. How is delay spread related to inter-symbol interference? Let us leave coherence bandwidth, it might be slightly complex. Let us look in time domain. Delay spread, okay? How is the delay spread related to inter-symbol interference? The symbol, if the symbol duration is less than the delay spread, if the symbol duration is less than the delay spread, then we will have inter-symbol interference, okay? Let me just briefly explain that again for some who are not, although I can see most of you are familiar with that concept of delay spread. So today we are going to talk about OFDM. Let me just take 5 minutes to explain why we need OFDM. As all of you already pointed out, let's say we have a base station which is transmitting to a mobile. As you have seen in the very first module, we have several paths, right? We have the line of sight component, we have the non-line of sight component, right? You have several copies of the same signal. You have some trees, you have some buildings, right? So these are known as, what are these known as? These trees, buildings, these are the scatterers, right? These scatter the wireless signal. These are the scatterers. These are the scatterers, correct? So you have your line of sight component, LOS, you have your non-line of sight component, another non-line of sight component which arises to the, and LOS means line of sight, NLOS means non-line of sight, which arises due to the scattering, which arises due to the scatterers. These scatterers scatter the signal, right? So what you have is basically you have multiple copies of the same signal, that is whatever is the signal transmitted by the base station, you get the direct line of sight component, also you get several scatter components, correct? You get several scatter components. Now what is the difference between these different signal copies? Are they of course they are copies of the same signal, but there will be different delays, and also what else? There will also be path loss, which means how do we characterize that? What do we say? Phase, the coefficient, the attenuation, right? The different signals will have different attenuations, right? Phase attenuation means complex attenuation, not just amplitude but also phase, correct? So they will have different attenuations, correct? So these different signal copies will have different delays, because the distances are different, correct? So the distances are different, there are going to be different delays, and they are going to, so for instance, let us take my favorite way to explain this as follows. So if I have, for instance, let's say you transmit correct, this is, let's say, your signal with symbol time t, correct, this is the signal which is arriving at the line of sight kind of component, correct. Then you will have another signal copy which is probably arriving correct. This is your delay tau 1, correct. Then you have another signal copy, let's say this is the first signal copy, this is the second signal copy, this is arriving with a further delay with respect to correct. So look at this, this is, let's say, your symbol S0, your symbol S1, S2, S3, S4, S5. So this is S0, S1, S2, S3, S4, S5. This is your again delayed signal tau 2. This is S0, S1, S2, S3, S4, S. Now what happens? Now all these signals, remember, they are adding up at the receiver. So if you look at any particular point of time, for instance, let's look at this particular point of time. You look at this S2 adding up with S1, adding up with S0. Yeah, S2 that is what is causing the inter-symbol interference. So these different symbols, right? S2, delayed version of S1 coming from one of the delayed paths, delayed version of S0 coming from the, these different things are adding up. Right? Which one? Which one? Oh, I don't know, whatever it is. I just, I don't think of these as zero levels or something of that sort. Think of this, let me just, these are just my drawing aids, don't confuse them. This is some kind, what I intend to say is, yeah, don't use this as the zero axis. These are just lines that I use for my drawing, helping me keep things straight. Yeah, okay. So now what you are getting, what I am trying to say is basically you have some different signals. Yeah, different attenuation. So some are, you can see some are more attenuated, some are less attenuated. The main idea is that these different symbols, right? The symbol, the current symbol arriving from the first path, right? The symbol, delayed symbol arriving from the second path, further delayed symbol arriving from the, all these things superpose at the receiver, like all these things superpose at the receiver, and this causes inter-symbol interference. So inter-symbol interference arises because of the multipath, but you can clearly see that it's not any kind of multipath or not any kind of all kinds of multipath components that cause inter-symbol interference. For inter-symbol interference to occur, you can see that this signal has to be sufficiently delayed in comparison to this one, right? the delay has to be comparable to the symbol duration, right? This signal, for instance, if this delay is very close to 0, then you can see it will still be the same symbols that overlap. So only when the delay of the successive arriving components, multipath components of the successive arriving paths sufficiently large in comparison to the symbol time or comparable to the symbol time or larger, we say that inter-symbol interference occurs. Because if the delays are small, this is characterized by the delay spread. What is the delay spread? Delay spread is basically the delay of the last arriving. For instance, here there is a first arriving component, there is a last arriving component which is arriving at tau 2. You can say approximately tau 2 is the delay spread. This is known as the max delay spread. What is the max delay spread? Max delay spread is the delay between the first arriving component and the last arriving component. That is known as the delay spread. If this delay spread, we will denote this by TD. If this delay spread TD is larger than T, this leads to inter-symbol interference. If the delay spread is large, that is what you have to remember. Why do we need OFDM? What is the motivation? The motivation for OFDM, as we are going to see later, is basically to overcome this distortion that arises because of inter-symbol interference. And why does inter-symbol interference occur? Inter-symbol interference occurs because the delay spread of the channel, right? The delay spread means the delay between first arriving component, last arriving component. The delay spread is greater than is comparable to or greater than the symbol duration T. Typically we express this condition as TD greater than T by 2. That is the typical rule of thumb we employ. That is, if the delay spread is greater than half the symbol time, which means that because the delay spread is greater than half the symbol time, the delayed signal, half of the symbol overlaps current symbol, half of the symbol overlaps with the previous symbol. Yeah, that's what it means. Roughly, if the delay spread, now there are various metrics for this. Yeah, there is no one, but some people say delay spread is greater than 1 symbol time, delay spread is greater than 2 symbol time. Right? Delay spread, roughly you can say that if the delay spread is greater than half the symbol time, if TD is greater, we call inter-symbol interference occurs if TD is greater than T by 2. If TD is greater than T by 2. This is the guideline. If TD is greater than or equal to T by 2, what is T? T is the what is TD? TD is the again you can look at my lectures, there are various notions of delay spread. What is delay spread? There is a maximum delay spread, there is an RMS delay spread and so on. There are different notions of delay spread, correct? So there are many ways to compute this metric delay spread. There is a notion of maximum delay spread, there is a notion of RMS delay spread, but roughly speaking delay spread is basically the delay, characterizes the delay profile of the wireless channel, that is the delay between the various multipath components, first arriving component, last arriving component. What is the delay between these? And the larger the delay, you can see the more problems it causes. Typically if the delay spread is greater than or equal to T by 2, where T is the symbol time, we say inter-symbol interference occurs. What is the typical delay spread in a wireless communication channel? Does anyone remember what is the typical delay spread, value of delay spread in the wireless communication channel? What is that? Not 1 divided by, don't tell me indirect answer. Tell me what is the approximate delay spread? 2 to 3 approximately, very good. Approximately of the order of microseconds, 2 to 2 microseconds, 1 to 2 microseconds. Yeah? Again, this is some approximate. Why does it arise? Because we know that distances are of the order of outdoor cellular scenarios, distances are order of kilometers, correct? So if you take 1 kilometer, divided by the speed of the electromagnetic wave, that is 3 into 10 to the power of 8 meters per second. Approximately you will get the delay spread of basically around microseconds. So 2 to 3 microseconds. Typical values of delay spreads are outdoor delay spread. Of course, indoor delay spreads will be smaller. Outdoor delay spreads will be typically around 2 to 3 microseconds. Is that fine? Outdoor delay spreads will be around. So this delay spread will be around. So delay spread is approximately 2 to 3 microseconds, and it can be larger also. Yeah, sometimes when you have very severe multipath, very severe scattering, delay spreads, for instance in LTE, they assume small delay spread, long delay spreads can be of up to 16 microseconds, right? They assume delay spreads up to 16 microseconds. Yeah, so delay spreads can sometimes be very large. Of course, that is worst case. It might still be. Typical delay spreads will be around 2 to 3, around microseconds, 2 to 3 microseconds. 2 microseconds is a good number. Yeah, okay. Now, what is the symbol time? Now, of course, we know symbol time depends on the bandwidth. Yeah, yes or no? Symbol time depends on the bandwidth. If the bandwidth is large, why do we need larger and larger bandwidth? So that we can transmit symbols at faster and faster rate, right? For instance, if the bandwidth is, let's say, we go to LTE or LTE, 4th generation wireless communication system, bandwidth is 10 megahertz. Bandwidth is 10 megahertz means, what is the symbol time? Symbol time will be 1 divided by 10 megahertz, 0.1 microsecond something, right? 1 divided by 10. So symbol time will be 1 divided by 10 megahertz. So bandwidth is so I have to say this bandwidth is equal to 2W. So that is the notion I am using. For instance, if this is W, this is minus W, this B equal to 2W is 10 megahertz, symbol time is 1 over 10 megahertz, that is 0.1 microsecond, and by symbols we mean complex baseband symbol. So each symbol will carry 2 bits. Yeah, so bit time will be half of the symbol. But don't worry, we are interested in complex symbol time. Okay, we are interested in what is it. You understand what is a complex symbol? Complex symbol means I channel, Q channel, right? I channel, Q channel, in phase quadrature, correct? Which means one symbol on the in phase, one. So it's actually 2 symbols. Yeah, you get my point. Actually speaking, it is 2 symbols, one complex symbol. B is equal to 2W. W is equal to, let's say, 5 megahertz. B is equal to 2W, that is 10 megahertz. Symbol time will be, complex symbol time will be 1 over 10 megahertz, correct? That is 0.1 microsecond. Okay. Now 0.1 microsecond is the symbol time. Delay spread is 2 to 3 microseconds. So you can see as the bandwidth increases, delay spread will be much larger than, what is our condition for intersymbol interference? TD is greater than T by 2. Now T by 2 is what? T by 2 is 0.1 microseconds divided by 2, correct? 0.05 microseconds. TD is 2 microseconds, 2 to 3 microseconds. So TD is significantly greater than T by 2. Yeah, you can see TD, everyone get the idea? TD is significantly greater than T by 2, and therefore this results in severe intersymbol interference. As the bandwidth of the communication system increases, the severity of the intersymbol interference increases due to the basically decreasing symbol time. Delay spread is same, because the delay spread depends on the scattering environment. Delay spread is same, right? 2 to 3 microseconds. Symbol time is decreasing as the bandwidth is increasing. Therefore, the severity of intersymbol interference is increasing as the delay spread is increasing. Severity of the intersymbol interference is increasing. Now, what do we have? What do we do? Therefore, what do we have? What do we do? Now, what can we do? If this intersymbol interference is increasing, because the symbol time is decreasing, what should we do then? What is the solution? What is the solution? What is the solution? Increase the symbol time. Very simple. Increase the symbol time. But then that is inefficient. If you increase the symbol time, bandwidth. I mean, why increase the symbol time? We already have a lot of bandwidth. Very good. That's a good solution. It's very simple solution, right? Because symbol time is decreasing, inter-symbol interference occurring. If you simply increase the symbol time, what is going to happen? Symbol rate is going to come down. Symbol rate is going to come down. So what is the solution? How to increase the symbol time without actually decreasing the symbol rate? You get my point? How to actually increase the symbol time without increasing the symbol rate? How can we achieve that? What is that? How do we achieve that? We have to transmit various symbols. That is very good. In parallel, we will increase the symbol time, but at the same time transmit several symbols in parallel over orthogonal channels. That is the main idea behind OFDM. What is the main idea behind OFDM? In OFDM, what do we want to do? Because the decreased symbol time is causing inter-symbol interference, we want to increase the symbol time. But if we increase the symbol time, just simply increase the symbol time, then symbol rate will be reduced. So what we want to do? We want to increase the symbol time, but transmit several symbols in parallel. We want to transmit several symbols in parallel so that overall the data rate is still the same, but each symbol has an increased symbol time. Is that clear to you? Yeah, each symbol will have an increased symbol time, but overall data rate will still remain the same. So what is the idea? The idea is increase symbol time. Idea is to increase. What is your idea? Idea is to increase but transmit several symbols in parallel. Increase the symbol time but transmit several symbols in parallel. How can we transmit several symbols in parallel? By using the notion of multiple subcarriers. So instead of single carrier transmitting a single symbol on a single carrier, what we are going to do is we are going to have multiple subcarriers and transmit multiple symbols. Transmit multiple symbols on multiple. So what do I have? I have this bandwidth minus W to W, which is of width B equals 2W, okay. I have one carrier, another carrier, another carrier, so on. I have one carrier, so what I am doing, I am dividing this original bandwidth B equal to 2W into n sub-bands. N sub-bands, what will be the width of each sub-band? If I divide it into n sub-bands, each sub-band will be of width B by n. So divide bandwidth B into n sub-bands. Each sub-band has bandwidth equal to B by n. We will call this as F naught, which is the fundamental frequency of the system. So first subcarrier is at 0, second subcarrier is at B by n, third subcarrier is at 2B by n, so on, minus B by n, minus 2B by n so on. Bandwidth of b by n minus 2b by n so on, minus b by n minus 2b by n and so on. So each subcarrier has bandwidth b by n, 2b by. So what is happening is basically you have your band b, you are dividing it into n subbands, and right, n subbands, right. Your original bandwidth of b, you are dividing it into n subbands, capital N subbands. So each subband, bandwidth of each subband will be b divided by n. So you will place, and you are placing the subcarriers in each sub. So first subcarrier, let's say your subcarrier is at 0. Next subcarrier will be at b by n. Next subcarrier will be at 2b by n. Next subcarrier at 3b by n. Again subcarrier at minus b by n, minus 2b by n. So you are placing subcarriers at b by n and multiples, that is integer multiples of b by n. We are calling this b by n as the fundamental frequency f0 of the system. We can call this frequency, we can call this this b by n, where we have these subcarriers, that is we are placing subcarriers at b by n, multiples of b by n. We can call this b by n as the fundamental, that is denoted by f0, which is the fundamental frequency of the systems. So these bands of bandwidth b by n are known as subbands, and these carriers, these individual carriers that we are placing in the various subbands, these are known as the subcarriers in the. So each of this is a subband, so you have a subband, and each of these is the subcarrier. So you can say we have subcarriers at f0 and k times f0, that is integer multiples of f0, subcarriers at k times f0, that is where k equal to 0, 1, 2, so on, and minus 1, minus 2, so on. And now what we can do, on each subcarrier we can modulate a symbol xk on each subcarrier. So what I am going to do is I am going to take my symbol x of k, modulate it onto the subcarrier e to the power of j 2 pi k f naught t, sum across all the subcarriers. So this is summing across all the subcarriers. Okay, you get my point. This is known as, so when you modulate xk on subcarrier k, this is known as loading the subcarrier. So what we are doing, we are taking x0 on subcarrier 0, x1 on subcarrier. So what we are doing is basically we are taking x0 on subcarrier 0, x1 on subcarrier 1, x2 on subcarrier 2, x minus 1, x minus 2. So we are placing x0 on subcarrier 0, x1 on subcarrier 1, x2 on subcarrier 2, x minus 1 on subcarrier minus. So this process is known as loading the subcarrier. So this process is known as, in OFDM, this is known as loading So subcarrier k is loaded with xk, and that is at multiple k f0, which is k times b by n. And then we are loading the subcarriers and taking the, so we are loading the subcarriers, taking the sum across all. We are loading the subcarriers, modulating them, taking the sum across all the subcarriers. taking the sum across all the subcarriers. Now let us say this signal I denote this by, let us say I denote this by, I denote this signal by x of t. I transmit this across the channel. I receive, let's say, y of t equals x of t. Consider initially an ideal channel without noise, without fading. That is no fading. No noise. Consider initially an ideal channel without noise, without any fading. Consider initially an ideal channel without any noise, without any fading. What is going to happen in this scenario? What is going to happen in this scenario? We have yt equal to xt. Now my point is, first let us talk about how to recover the symbols xk, or how to recover the symbols xl. Yeah, tell me. Only one symbol per subcarrier. See, we'll come to that. We'll come to that. I'll talk about that. Let us first say we are transmitting one symbol per subcarrier. Obviously, we can transmit more symbols per subcarrier, but not at the same time. Different time instants. But what is the time? How much gap do you need? So we are loading. So what he is asking is, we are loading the subcarriers with one symbol each. But does that mean we can only transmit one symbol per subcarrier? Right? But that will be wasteful, right? We can load one symbol at a given time. After some time we can transmit one. But what is the time gap that has to be there? That is something that we have to find out. That is a valid question. So that is something that you have to find out. Now for that we have to understand how to recover the symbol xk or xk, these various symbols loaded on the subcarriers, modulated on the subcarriers. How can we get them back at the receiver? You sum the signal you transmitted. How can we get them back? How can we get them back? Now if you look at that, this reminds us of something, right? What is the xk e to the power of j 2 pi k f naught t? What is that similar to? Is similar to the Fourier series, discrete Fourier series, correct? Discrete Fourier series, right? Periodic signal can be represented as sum ck e to the power of j 2 pi k f naught. This is the discrete. Which means ck is the Fourier series coefficient. How can we extract ck? Inverse Fourier. Okay, how do we get that? Very good. How do we get that? If I want to find x, so my question is, if I want to find xl, how do we get it from this? What should I do? This is my signal xt equal to yt. So I have received yt. How can I find xl? What should I do? Multiply yt e to the power of minus j 2 pi l. If you want to find xl, right, I have to multiply yt e to the power of minus j 2 pi l f naught t integrate 0 to what time? 0 to what is the time? Does everyone remember discrete Fourier series? Inverse, how to find the Fourier series coefficient? Which one? 1 divided by no, 1 divided by capital T. No, I am asking integrate from 0 to where? Integration limit. No, not 2 pi, 0 to symbol. Yeah, symbol time, but what is the symbol? What will be the symbol time here? 1 by f naught, which is the fundamental time, not the symbol time. Symbol time is different, something different. 1 divided by f naught, right? Because fundamental frequency is f naught, right? Fundamental frequency is f naught, right? Each of these subcarriers is basically periodic with 1 over f, right? It's 1 over f naught is a fundamental period. So I integrate it over 1 over f naught, and then I also have to multiply by f naught, or basically 1 over t. 1 over t is, don't get into 1 over t, because 1 over t is, we have to still define what is the, there are different times, yeah, what is the symbol time, what is the sample time, okay. Now f naught integral 0 to 1 over f naught yt e to the power of minus j, because if you do that, if you substitute yt, what will we get? F naught 1 over f naught, yeah, let me just get this thing erased. So if you substitute this, let us substitute yt equals summation xk e to the power of j 2 pi k f naught t e to the power of minus j 2 pi L f naught t, yeah, उसको भी erase कर दीजिए उसको, and then what will you get? This will be equal to, if I interchange the order of summation and integration, summation k xk f naught 0 to 1 over f naught e to the power of j 2 pi yeah, and this quantity e to the power of j 2 pi integral 0 to 1 over f naught, that is integration over one fundamental period, right, integration over one fundamental period 0 to 1 over f naught e to the power of j 2 pi k minus L f naught into t. Now what is this integral? This integral will be, this is equal to, that is if you are taking a sinusoid, complex exponential, integrating it over one fundamental period, what is it going to be? If a0 if k is not equal to L, right? If you integrate sine wave over one period, cosine wave over one period, what are you going to get? You are going to get 0, right? Unless k equal to L, in which case it is simply 1, and this integral will be 1 over f naught into 1 over f naught, that will be 1. So this quantity here will be equal to summation k xk into delta k minus L, which is basically equal to x of L. That is, what we are doing is basically we are multiplying by e to the power of minus j L f naught t, integrating it over one fundamental period 0 to 1 over f naught. Now if that means if k equal to L, you get back x of L, if otherwise all the other x's are, all the other basically all the other subcarriers integrate to. And this is the property that we are using. Look at this. What is the property that we are using? We are using this property that this integral is equal to 0 if k not equal to L, and that is if you look at this integral f naught into this is equal to 1 if k equal to L. This is the property of, what is this property? This is the orthogonality property, that is the different subcarriers e to the power of j 2 pi k f naught t e to the power of j 2 pi L f naught t, these are orthogonal, yeah, these different subcarriers are orthogonal. And as someone pointed out, how does it help us? It helps us because now we don't need to space the different subcarriers with a gap between the different bands, between the sub bands. We can have sub bands which are placed adjacent to each other because we are employing the property of subcarrier orthogonality. So this is basically the orthogonal subcarriers. This is basically the orthogonal, the concept of the notion of orthogonal subcarriers. So the different subcarriers are so that is why we get the name orthogonal, frequency division, multiplexing. So the different, so frequency division, what is frequency division? We are dividing the frequency band into different subcarriers. These subcarriers are orthogonal. Multiplexing, we are multiplexing several. How are we multiplexing? By loading the symbols onto the subcarriers at the same time. And now you can see what is the time interval. What is the time interval for each symbol on the subcarrier? What is the time interval? Time interval is, you can see 0 to 1 over f naught, correct? 0 to 1 over f naught. What is f naught? F naught is b by n. F naught is b by n. So what is 1 over f naught? N by b. Okay, you can see that. So what is the symbol time? The OFDM symbol time that we talk about. OFDM symbol time. This is equal to 1 over f naught equals n over p. N over p. 1 over f naught, that is n over b. What is b? B is equal to bandwidth, that is 2w n over p. For example, let us now take a simple example. Let us go back to our case, b equal to 10 megahertz. B equal to 10 megahertz, let us say 1020, we have 1024 subcarriers. So if B is equal to 10 megahertz and we have 1024 subcarriers, what is the symbol time? What is the OFDM symbol time? What is the symbol time for each subcarrier? What is the OFDM symbol time? N by B, 1024 divided by 10 megahertz. What is that going to be? 1000 mega 24 divided by 10 megahertz is going to be how much? 10? No, not 10, 102.4, correct, 102.4 microseconds. So the OFDM symbol time is 102.4 microseconds. So if B equal to 10 megahertz, OFDM symbol time is 102.4 microseconds. Okay, so B equal to, if B equal to 10 megahertz, OFDM time equal to 102.4 microsecond. And remember, that is what we wanted to do. What did we want to do? We wanted to increase the symbol time. How much? So symbol time is how much? Now look at that. Delay spread was 2 microseconds. Originally symbol time was 0.1 microseconds. Now we have increased symbol time to 102. So now symbol time is much greater than the delay spread. So will there be any intersymbol interference? There will not be any intersymbol interference. Why? Remember, what is the condition for intersymbol interference? Condition for intersymbol interference is TD greater than T divided by 2. TD is 2 microseconds approximately. T by 2, originally it was T by 2, T was 0.1 microsecond. Now T has become 100 microseconds. So T by 2 is 50 microseconds. So TD is much smaller than T by 2. So intersymbol interference is insignificant. That is what we can say. Intersymbol interference is insignificant. It will still be there, but it is insignificant in comparison to the OFDM symbol time. And therefore what we have is, we have these different, what have we done? Previously we were transmitting multiple symbols, that is each symbol 1 by B, so on. Yeah, you get my point. Previously what were we doing? We were taking multiple symbols, each symbol of symbol time 1 by b. Now what are we taking? Each symbol is of symbol time n by b, but then we are transmitting n symbols in parallel over the n subcarriers. So now we are multiplexing in frequency domain. So each is of time n by b and you are transmitting this is multiplexing in the frequency domain. So previously you had symbols, you are transmitting first symbol 1 by b, 1 by b, 1 by b, 1 by b. So this is multiplexing in the time domain. Now you are multiplexing in the frequency domain. Time you are expanding, frequency you are multiplexing the. So you can think of this as all frequency time 1 by b. This is frequency b by n time n by b. And therefore now if you look at the data rate, what will be the data rate? Data rate of this will be b, 1 by b, complex symbol, right? Data rate is b. This is symbol time n by b, but n symbols, again data rate. So data rate will be the same. Okay, that is what you have to understand about OFDM. Data rate will be the same, okay, but OFDM is much more convenient. That is, orthogonal frequency division multiplexing is much more convenient because of the intersymbol. Yeah, tell me. No, as n increases, that's in fact a misconception. People think that as the number of subcarriers increases, data rate. But is that correct? Is that correct? That is not correct, because in a single carrier system also we can get the same data rate. But what happens is, because of the inter-symbol interference in a single carrier system, it will become more and more difficult because of the inter-symbol interference. The distortion will become more and more significant as the bandwidth increases. That is the problem in a single carrier. But strictly speaking, will the data rate increase? Strictly speaking, will the data rate will not increase, because in a single carrier system you are transmitting one symbol per time 1 by b, right? So data rate is b. Multi-carrier system, you are transmitting this OFDM system, you are transmitting, it's also a multi-carrier system, you can transmit n symbols, one symbol in time n by b, but you are transmitting n symbols over the n sub-carriers. So net you have n divided by n by b, that is again rate of b, that is again the rate of b. So symbol rate will be constant between single carrier system and multi-carrier system, symbol rate will be constant. Now what is the problem? The problem is that first subcarriers, there are two problems. First subcarriers, what is the problem? If we have to generate n subcarriers, we will require n modulators, n demodulators. How do we address that problem? How do we address that problem? That solution is very interesting. If we look at this, now you have to understand what is done in OFDM. If you look at your signal x of t equals summation k e to the power of a k j 2 pi k f naught t, what can I do? This signal is bandwidth b. I can use the Nyquist criterion. I can sample it at, what is the sampling time? Sampling frequency is fs is equal to 2w equals b. Okay, so the sample, if I look at the sample of this signal, so sample of the signal, if I look at mth sample of the signal, mth sample of the signal will be at x, m times the sample time equals x m times 1 over fs equals x m over b, which is equal to summation over k xk e to the power of j 2 pi k f naught t is equal to m divided by b. Now substitute f naught is equal to b divided by n summation k xk e to the power of j 2 pi k b divided by n m divided by b, b cancels, so what we have is summation k xk e to the power of j 2 pi km divided by n, and what is this? This is equal to x of m. And if you look at this expression, what is this expression? This expression is the expression of the, what is this expression? You are familiar? What is this expression? This is the expression for the IFFT, IDFT, or yeah, yes or no? Correct? If I sample, how am I getting this? I am replacing the sampling it at what rate? 2W equals B. If I sample it at 2W equals B, what is the sampling time? TS equals 1 over B. That is basically your 1 over Fs. So mth sample will be at m times Ts, m over Fs, that is m over B. So you have xk e to the power of j 2 pi k f naught. Instead of t, I am substituting m over b. F naught is b over n, so b cancelled, so e to the power of j 2 pi k m divided by n. That is what I have, and this is the expression for the IFFT or IDFT. IDFT, which is basically nothing but IFFT. IFFT is basically fast algorithm for, it is a fast algorithm for implementing IFFT. It is a fast algorithm for implementing IFFT. Okay, IDFT is nothing but it's a fast algorithm for implementing IFFT. Okay, okay, it's a fast algorithm for implementing. Yeah, is that fine? Okay, okay, yeah. So what are we saying here? What is the interesting thing? The interesting thing is we can generate the OFDM signal using IFFT. We don't need the modulators. We don't need the N modulators, right? We can generate the signal using IFFT. Similarly, we can demodulate the signal using the FFT. So at the signal, once we load the subcarriers, what is the point? The point is at this, when we are loading the subcarriers, we don't need the modulators. We can simply use the IFFT. We can use the IFFT to generate the sample. You get my point? So what are we doing? So what is the OFDM schematic going to look like? You have the serial symbols x0, x1, xn minus 1. You convert them to parallel, serial to parallel. Load them on the subcarriers. Then what do you do? After loading on subcarriers, IFFT. then what do you need to do? You need to convert parallel to serial, then you transmit. Serial to parallel, IFFT, parallel to serial. At receiver, again serial to parallel, FFT, parallel to serial, detection, or basically detection and parallel to serial. Okay, so basically that. So that is a block diagram. Basically what you are doing, you are taking how many symbols at a time? You are taking n symbols at a time. Okay, n symbols. What is the sampling time? Sampling time is sampling time is, remember what is your sampling time? So there are two times in the OFDM symbol. Okay, you should not get confused. One is the OFDM symbol time that we talked about. What is that? That is equal to n divided by b. That is the OFDM symbol time. That is what we have written over there, n divided by b. Then there is a sample time. Sample time is, what is sample time? 1 divided by b. That is the OFDM sample time. That is the sample time of the OFDM system. So in an OFDM system, that is why when you said time, I said you should not get confused. OFDM symbol time equals n divided by b, OFDM sample time equals 1 divided by b. OFDM symbol time equals n divided by b, OFDM sample time equals 1 divided by b. So there are two types. If b is equal to 10 megahertz, number of subcamples is equal to 1024, OFDM symbol time is 102.4 microseconds. What is the OFDM sample time? 1 divided by 10 megahertz, that is 0.1 microsecond. So the sample time is 0.1 microseconds, symbol time is 102.4 megahertz. This is the OFDM sample time. This is the difference between the symbol time and the concept of symbol time and sample time. You have to understand the difference between the concept of OFDM symbol time versus OFDM sample time. Okay? Yeah, tell me. Correct. It is not time domain symbol. See, it is not time domain or frequency domain. If you look at it really, it is just calling it frequency domain for convenience, but it is simply the sample signal on the subcarriers. Both are time domain only. Yeah, both are time domain only. But it is convenient to think of XK as the capital XK as the frequency domain symbols which are loaded onto the subcarriers. Then you are converting it into the samples which are transmitted in the time domain. At the receiver, again you are taking these samples in the time domain, performing FFT, converting them back to the frequency. It is convenient to think of it that way, but the operation is all happening in time only. There is nothing, it is just a way of generating the multi-carrier signal. It is a way of generating the multi-carrier signal. Okay? What happens if the FFT is used? That is a complicated question. What happens if the FFT is used? That is a very complicated question. You think about it, what happens if the FFT is used? You think about it. It's an interesting question, but it's a complicated question. What will happen if the FFT is used? Yeah.
Actually, here the incoming all like digital bits only.
Which one?
The incoming symbols, they are in binary.
Which one? They are the digital symbols, correct. X0, X1 up to Xn minus 1, correct.
So if I tell one symbol, meaning every symbol is represented by n samples.
Every symbol is represented by?
N samples.
N
samples.
Which one?
N bits. And each of these bits is loaded on the tag.
No. See, we have complex symbols. Complex symbol can be any number of bits. For instance, it can be complex symbols such as BPSK. BPSK is of course real. QPSK. QPSK means each with one bit on real, one bit on imaginary. Right? it can be 16 com. 16 com means basically 16 symbols, means 4 bits total, 2 bits on real, 2 bits on imaginary. It can be 64. It depends on the modulation. Yeah, so the complex symbols can belong to any modulation, any type of modulation. Depending on the modulation, that will decide the number of bits per complex symbol. Okay, fine. Yeah. Okay. Okay. So that is one of the aspect that is basically related to the IFFT and the FFT. After the break, we will look at what is the concept of cyclic prefix and then how to do optimal power allocation in an OFDM system. Yeah, we will look at how to do optimal power allocation in the OFDM system. Yeah, we can do that.